We're live.
So Steven, can you see the feed?
Oh yeah, I'm looking right at it.
Perfect.
Hello. Yep, yeah, I'm fine.
Okay, and Rob is here, so I guess we can get started. So welcome to this coast-to-coast thesis offense of Miles Lubin. So I guess it's customary for the advisor to say a few words, and I guess I could really spend too much time talking, but actually I guess I also can make it short. So Miles was an award-winning researcher even before he came to ORC. He actually does award-winning research as a hobby. So jump, for instance, and I guess I was looking at all the papers that are not included on the thesis, and I think probably there's maybe one or two extra theses there. So we're just going to see a portion of what Miles has been producing over the years. And the last thing I wanted to say is it's a pleasure to work with Miles. He's also a really good communicator. I've seen him give talks in English and Spanish, and actually not Spanish, but Chilean. He actually included all the Chilean slang and some typical dishes in a tutorial he gave in Santiago after being maybe less than a week in Chile. So with no pressure, I give you now Miles Lubin.
Thanks for the introduction. Thanks for everyone coming. Thanks to my family for coming. So I'll just jump right in with defining an optimization problem, which hopefully everyone has seen before. The problem that we're going to think about is that we're given some set S. We'll call it a feasible region. We have some function f that maps from the set to the real numbers, and we would like to find an element of the set with the lowest possible value of f of x. And if we do find this element, and if it exists, then we'll call this a global optimal solution. So how do you go about solving this? Well, what a lot of people do is just use heuristics, do a local search, play around. That's probably potentially what a majority of people do in the real world to solve these kinds of problems. What we tend to do in operations research is instead to either approximate or reformulate, if you're lucky, these problems in a form that we know how to solve to a global optimal solution. So which are the optimization problems classes that we know how to solve to a global optimal solution? I would claim that this includes convex optimization, which is efficient both in theory and practice. And I'd also say that it includes integer programming, which is hard in theory, but in practice we can solve problems that people care about in a reasonable amount of time. So in the thesis, we're going to consider a generalization of both of these categories of problems, which is mixed integer convex optimization, or I'll call it MICP. These are optimization problems which are, you start out with a convex problem and you add the constraint that some subset of the variables needs to take integer values. And what we're going to do is look for methods that deliver global solutions, or at least give us globally valid bounds on these solutions. So MICP is a very natural generalization of MILP, mixed integer linear programming. I was doing a bit of research, and the earliest papers in the 60s, they were proposing methods for convex optimization and MICP at the same time, even though MICP hadn't really, well, nothing had taken off at that point, but MICP still hasn't taken off. MILP, I would say it's mature and widely used. MICP, I would say it's not, maybe except for the case of MISOCP, which already has support by certain commercial solvers. So Bonami et al. In a review a few years ago stated that even though the advances in MILP have translated into advances in MICP, there's still a large gap in the size of problems that can be solved reliably in a reasonable amount of time. So we'll see that MICP methods make use of MILP methods, or they can, but so far this hasn't translated into MICP being as easy to solve as MILP. which itself is hard to solve, but at least we'll consider those as problems that we can solve. Okay, so why is that? So if you're skeptical, you might propose two different reasons. You might say, well, maybe MICP is just much harder than MILP. That could be true. And you could also say, maybe it's not that hard, but maybe there's not enough motivation to actually solve these problems in practice. My response to those 2 points would be, first, well, maybe MICP is harder than MILP. I would say traditional MICP approaches, what people have been looking at since the 60s, 80s, 90s, have been based on nonlinear programming, NLP, the KKT conditions under the name of convex min-LP. On the other hand, Bental and Nemirovsky suggests that NLP is obsolete as a basis for convex optimization. I won't state that as my claim, but it's an interesting claim to consider. Instead, they propose what they call modern convex optimization, which is based instead on conic duality and using some cones that we understand. And a lot of the key advances that we make in the first chapter are really just making some simple connections between modern convex optimization and MILP. And we took these ideas and we turned them into a solver, and we were able to solve some open benchmark instances just by making these simple connections. So that would tell me that there's potentially room for a lot of improvement here, because this is the connections between modern convex optimization and MILP haven't really been explored yet. So, okay, maybe I convinced you that it's not too hard, but maybe there's still no reason to solve these problems. So in the same review paper, Bunami et al. Cite portfolio optimization, block layout and manufacturing, network design, and design and control of chemical processes as either potential applications or real applications of convex min-LP. In power systems, applications that I'm personally familiar with are if you start working with chance constraints, you end up with tractable approaches for chance constraints, leads you with second-order cone or semi-definite programming constraints. If you add scheduling decisions on top of that, then you immediately have a mixed integer convex problem. Or if you use convex approximations of power flow and you would like to make scheduling decisions on top of that, then you can pretty easily write that down as a mixed integer convex problem. There's a growing literature, which I haven't nearly surveyed, but on cardinality constrained statistical estimation problems. So convex optimization has played a big role in statistics. As soon as you add in some discrete constraints on top of your, let's say, regression problem, then you could end up writing those problems as mixed integer convex problems. Genetic sequencing, this was actually a paper that cited one of our very recent papers. I'm not sure exactly what they're doing, but it seems like a cool application. Obstacle avoidance, that's an example. I'll give you a little bit more detail on that on the next slide. And then finally, in chapter 4, we're going to study the scope of MICP from a more theoretical perspective to try to understand what is the class of optimization problems that you can solve or that you can put into MICP form. Okay, so just a little fun example. If you're familiar with sum of squares optimization, you can think about mixed integer sum of squares, and you would get this problem, for example, if you model a trajectory as a polynomial, impose constraints on that trajectory, you can formulate those approximately using sum of squares optimization, which ends up as semi-definite programming. If your control decisions have a discrete aspect, for example, minimize the number of times that you decide to thrust, then now you have some integer constraints and you have a mixed integer sum of squares problem. There's definitely not a class of problems that people have been trying to solve, because semi-definite programming is still kind of hard. Mixed integer semi-definite programming is even harder, but this is something that we can start to think about solving. And I'm talking about this because Joey Hutchett gave a recent talk at SIAM conference on optimization And he generated this figure by using our solver to model an obstacle avoidance problem where you have to go above or below certain obstacles, and you can choose to insert thrust at certain periods of time. This is a MISDP problem, and it's just a kind of cool application of the software that we've already written. Okay, so let me get into the body of the talk. This chapter's work with Emery Yumangil and Russell Bent from Los Alamos. And the key points, I'm going to go through this chapter quickly because I think the committee's most familiar with this work, is that extended and lifted formulations can greatly accelerate polyhedral outer approximation methods. I'll explain all of that. Mixed integer conic form ends up being a very natural encoding of extended formulations. And in order to get into mixed integer conic form, disciplined convex programming comes along in terms of a modeling concept that people can write down an optimization problem and ends up into the structure that we want to solve it in. And finally, we solved open benchmark instances by pulling these ideas into a piece of software called Pajarito. So put up a picture of Emery, Russell, and Juan Pablo at Pajarito Mountain, which is the namesake for the solver. Okay, so we'll define a general MICP problem in the following form. We're going to minimize over the space of Rn some linear function C transpose X subject to X belonging to script X, some closed convex set, and some, on top of this, we have the constraint that a subset of the variables must take integer values. And we can always assume that this objective function is linear because any convex objective function can be rewritten as a constraint by using the epigraph transformation. So this is just our general form, and you note that if we drop these constraints on the integer variables, and we have a nice convex optimization problem. So how do people go about solving these? There's a few different methods. The most straightforward method is just plain branch and bound, where you would recursively partition the assignments to the integer variables, and at each partition, you would solve a convex relaxation to help you prune the search tree. This was proposed in 1985 for the context of MinLP, but it's a very direct analog of the methods that people use for mixed integer linear programming. What we're going to look at in this chapter is iterative outer approximation, which takes a pretty different approach. We're going to build a polyhedral relaxation of the convex constraints, and then develop a sequence of mixed integer linear relaxations and convex subproblems that will eventually give us a globally optimal solution. And this was proposed in the context of convex MinLP in 1986 and has been refined and is present in Bondmin, which is an existing solver. And then in the next chapter, we're going to look at an improvement to the iterative outer approximation algorithm, which is LP-based branch and bound, where we're working with a single branch and bound tree, but instead of using convex relaxations, we use LP relaxations, and then we refine them by solving convex problems at certain points in time. Okay, so how do we develop a polyhedral relaxation of a convex set? If you happen to write down your set in the form of the X is satisfying that g of x less than 0 for some set of convex functions gj, and if g is smooth and defined over all of Rn, then you can write this following equivalent definition of x as x is the infinite intersection of half spaces, and these half spaces are obtained by picking a point in Rn, linearizing the function at this point, and since you know it's convex, you know that the function lies above the tangent to that point. And so this is a semi-infinite description of the set. To get a polyhedral relaxation, all you do is take a finite subset of these points. You'll have a finite intersection half spaces, which is a polyhedron. So generalizing a little bit, let's say you have any sort of polyhedron which contains your convex set, then you can think about writing the following optimization problem, minimizing C transpose X, the same objective function, over the polyhedron. This is a relaxation of your convex constraints, and you keep the integer constraints in the problem. So this is a mixed integer linear relaxation of the problem that we'd like to solve. So the basic algorithmic idea is, well, let's solve a sequence of these problems. Every time we solve this, we'll get a lower bound. We'll refine the polyhedral relaxation until we have a feasible solution that matches our lower bound. Then we're done. So I won't go into more detail about this algorithm, but that's the basic idea. So just an illustration of what might be going on. If your integrality constraints is that you would like the first component, the x component, first component of x to be integral, and you'd like them to belong to this ball, you might start out with one half space. That's a valid relaxation of the ball. If you optimize the integer constraints over this half space, you would end up with x star. You come up with a smart way to cut off x star, and if you add this particular hyperplane, you now have this polyhedral relaxation has two hyperplanes. If you optimize over it, you would get this x prime point here, which would prove global optimality because you'll have a feasible solution that also is feasible to the relaxation. Okay, so that's the algorithm. People have been using it. It works, kind of. But what can go wrong? What can go wrong is that since you're basing these polyhedral relaxations on gradient linearizations, it could be that you just need way too many of them to get a good approximation of your convex set. So just to motivate this, even though it's in the non-smooth case, think about the L1 ball. Very standard example that to represent the L1 ball as a polyhedron, you need 2 to the n hyperplanes in the space of the original variables. But if you've taken a linear programming class, you know that you can introduce n extra variables, and you'll end up with a formulation for the L1 ball that has 2n plus 1 constraints. So just by introducing extra variables, that enables us to write down a polyhedron that's much smaller and represents the same set. So more recently, people have looked into what happens in the smooth case, and it turns out that a very similar thing happens for the L2 ball. So Hijazi developed an example where you have an L2 ball centered at 1/2, and the radius is designed such that this ball contains no integer points. It also has the property that any line segment between points on the integer lattice will go through the ball, which means that if you have any hyperplane which separates a point from the ball, then and any hyperplane can separate at most 1 point from the ball, which means you would need 2 to the n hyperplanes to come up with a polyhedral relaxation of the ball, which contains no integer points. So this means that if you were running this algorithm, for it to tell you that there's no feasible solution to this problem, it would take 2 to the n iterations. And the fix is also very similar. You introduce extra variables. You split apart the terms in the sum, and you can write down a polyhedral relaxation in the space of x comma z that needs only 2n hyperplanes to exclude all integer points. Okay, so that's the simple idea. What about how do you actually turn this into practice? It turns out, I won't be able to go through these points in detail, that mixed integer conic form is a representation of the problem which encodes extended formulations in a very natural way. So if your problem is written in conic form, I'll define conic form in a bit, then you've already encoded, you've already done these transformations or exposed the information that allow us to do them. And to get a problem into mixed integer conic form, disciplined convex programming provides a systematic approach for transforming algebraic expressions into conic form. So you can use software like CVX, CVXPy, ConvexJL, and you write down an algebraic expression, you follow the rules of disciplined convex programming, and it will generate a mixed integer conic form problem, which has these properties that we like. So I'll still define conic form in a little bit later, but if you're thinking about encoding problems in conic form, you could ask, well, which cones do you need to use to write a problem down in conic form? So you can start out with a non-negative orthint, which is a nice cone. You can write down any linear programming problems just as optimization problems over the non-negative orthint. Then you go towards the second order cone, which is the epigraph of the L2 norm, the exponential cone, the PSD cone of a positive semi-definite symmetric matrices, and the power cone, which is another cone out there, though less studied and less used at this point. So what we did is we took 333 benchmark problems from the MinLP lib2 library. They're convex MinLP problems, so they were written ignoring conic structure, not even thinking about cones, and we classified them according to which cones you actually need to represent them as mixed integer conic problems. And it turns out that 217 of them only need the second order cone. 107 of them only need the exponential cone, so they might have logs, exponents, entropy function, log sum of x. These are all functions that you can write down in code using the exponential cone. 7 of them needed a mix of the second order cone and the exponential cone. 2 of them would be written down using the power cone, and that's it. These are all of the cones that were needed to represent these problems in this benchmark library. So I'll mention that these problems in this second order cone only category are mixed integer second order cone problems, so you can solve them using existing mixed integer second order cone solvers. There are no commercial solvers that support exponential cones or mixes of exponential cones with the second order cone. So we took this and we used these ideas to solve a couple open problems in the benchmark library. So GAM01 requires a mix of second order cones and exponential cones. It has 145 variables, 1,200 constraints, most of which are linear. We, using our solver Pajarito and the iterative algorithm in 6 iterations, using Cplex as the MILP solver, Nitro as the convex. Here we end up using it as an NLP solver. We proved that the global optimal solution is 21,380, and previous attempts at this instance had found the best lower bound of 1,735 and a best solution of 21,500. So we were really able to close this gap by getting better lower bounds from better polyhedral relaxations of these convex sets. TLS5, TLS6 are pure second order cone representable. They've been unsolved since 2001. And in less than 24 hours, we were able to solve them using Gurobi. So all we did was take these problems, write them down in mixed integer second order cone form, hand them off to Gurobi, and we got the solutions to these problems. So you can tell that people were not thinking about cones when conic representability when they wrote down these benchmark instances. Over the whole benchmark library, we ran an experiment where we translated 194 of these problems from MinLP-lib into convex.jl. Convex.jl gave us a mixed integer conic form. Then we ran our algorithm, iterative algorithm, and in aggregate, the number of iterations we need was 994. If we compare this with BonMin, which is an open source convex MinLP solver, which implements a very similar algorithm, the total number of iterations that they needed was 2,600. So we were able, I would attribute this to the extended formulations, giving us better relaxations. Therefore, we need fewer iterations to solve these problems.
And you're counting iterations how?
One iteration ends up being one MILP solve and one convex subproblem solve.
Either or both together?
Both.
Okay.
Both. Yep. So final convergence note, the iterative outer approximation algorithm makes some assumptions on strong duality holding in certain convex subproblems. We were able to find an example of a problem that actually cannot, we can prove that it cannot be solved by the iterative outer approximation algorithm because there is no polyhedral relaxation of the convex constraints that gives us the right objective value. So that's just an interesting note and opens up some maybe further questions if we haven't yet run into problems where this shows up in practice, but if it does, there's some motivation to think about how to deal with this. Okay, so the next chapter is work with Chris Coey. And here we're going to take conic form, mixed integer conic form as the starting point. So we're going to forget about convex min LP, forget about DCP. We're just going to say, let's start off with mixed integer conic form and write a good solver for that. So again, we'll switch notation a little bit. We're minimizing the inner product of C and X, so C transpose X. And we're going to write down our conic constraints as some affine transformation of X belongs to some cone, and we have some collection of cones that we need. So here, when it's necessary, this includes polyhedral cones. This could include equality constraints, linear constraints, nonlinear constraints. And when we need to, we'll separate them out. But for here, you can just write everything down as a cone. All the convex constraints as a cone, and we have integrality restrictions on a subset of the variables. So what we can do, the methods that we're going to develop end up being pretty general. They can handle any closed convex cone or a product of closed convex cones. But in particular, we can handle mixed integer second order cone programming, mixed integer semi-definite programming, and all of that combined with the non-symmetric exponential cone. So if you're going to think about polyhedral approximations of cones, you should start out by looking at the dual cone. So if K is a closed convex cone, then the dual cone precisely defines the set of hyperplanes which outer approximate this cone. So this is an if and only if. You can say Y is in your cone if and only if Y satisfies this potentially infinite collection of linear constraints. So we can obtain a polyhedral outer approximation for each cone by just picking a finite subset of elements of the dual cone, and we would write down the linear constraints as just enforcing that finite subset of elements of the dual cone. And to put a name for this, we'll say that an element of the dual cone induces a K-star cut. Since we're in the MIP business, MIP people like to talk about cuts. So we'll call this an element of the dual cone will give us a K-star cut.
So even though K star is not in your formulation, right? All your cones are CKs.
Right. So K
K-star cone.
K is a generic cone. CK is a particular cone. Yep. So you can ask, well, what are these dual cones? For the second order cone and the PSD cone, these cones are self-dual, which means that the dual cones are the sets themselves. This is a very useful property for developing theoretical algorithms for solving these convex optimization problems. For us, it doesn't make a big difference. For example, the exponential cone is not self-dual, but as far as we care, it doesn't make a big difference. And what's very, very useful about thinking about outer approximation using K-star cuts is that you have a very easy way to validate if a cut is valid. Someone gives you a vector, you can test if it's valid by just testing if it's in the dual cone. That's very easy. You can know which direction, you can tweak the coefficients of this cut. Again, useful for writing a solver just by thinking about projections onto the boundary of the dual cone. So if you're writing a solver, it's very nice to be able to validate if I rounded this cut a little bit, is it still valid? Yes or no? It's a nice property to have. If you're going back to gradient inequalities, it's a much more difficult situation. If this is the only structure you have is the gradient inequalities, it's the only way that I'm aware that you can validate if if a linear constraint is a valid gradient inequality is by demonstrating the point at which you would linearize, which is much harder to validate in practice. So how do we go about generating these K-star cuts? The first thing we can do is solve the continuous relaxation. So this problem on the left here, what we've done is relaxed the integrality constraints. And on the right-hand side, we have the standard conic dual of this problem. And if we solve this primal dual pair to an optimal solution, no duality gap, everything's attained. Well, actually, any feasible points to the dual will give us K-star cuts because they're in the cone. If they happen to be solutions that correspond to the optimal solution, we have this nice property that the points which satisfy that set of K-star cuts is bounded in the direction of this objective value. So you cannot have a solution that both satisfies these K-star cuts and has an objective value less than the convex relaxation. So that it's also a nice property computationally because you know that if you add these cuts, then your polyhedral relaxation will be bounded. You don't have to think about dealing with unbounded relaxations. What we can also do is generate K-star cuts from solving different continuous subproblems. So if we look at how to generate these by, if we look at problems that might come up in a branch and bound procedure, for example, restricting, we're still relaxing integrality, but we're restricting the components of x maybe to belong to some box, or to be fixed to a certain value. When we solve these problems, we also get cuts that have a nice property, and I'll skip defining that property exactly, but it ends up being a useful property that we can prove convergence of our algorithm with. So those two classes of cuts from solving the continuous relaxation and from solving subproblems should be compared with separation cuts, which we'll call them separation cuts. It's a very standard class of cuts that people use in practice. If you have a point that's not in the cone, these cones are closed and convex, we can write down a separating hyperplane. If we need to, the separating hyperplane can always be shifted into a K-star cut. So really, any cut that separates a point from the cone is a K-star cut. So for example, if you have a symmetric matrix that is not PSD, so it has some negative eigenvalue, take the eigenvector corresponding to that negative eigenvalue, take the rank 1 matrix generated by that eigenvector, and then the product of eigenvector with your matrix T will give you a negative number. But that's problematic because this rank 1 matrix is an element of the dual cone. So it's a valid K-star cut. So this is a K-star cut that separates T from the set of feasible solutions. So skip STP uses this class of cuts for MISTP problems in an LP-based branch and bound method. Skip, Gurobi, Cplex, and Express use separation cuts in the context of MISOCP. Okay, so the cuts that were just presented from solving conic subproblems are new in the context of conic optimization. They are kind of analogs of cuts that people have developed in the convex min-LP case, but they haven't been stated in the conic form. Separation cuts, on the other hand, they're well known. They're very easy to compute, particularly maybe it's an eigenvalue decomposition, or even easier, you don't need to solve a convex problem. And these are the cones that are used. These are the cuts that are in existing solvers today. On the other hand, these cuts are used, but I haven't seen anyone write down an algorithm that's provably convergent using these cuts. And that means you need a finite number of steps to get the global solution. I haven't seen anyone write that down in a general way. But the folklore is that it doesn't really matter. Just use these cuts. Eventually, you get close enough to the solution, and it works. Which is not too far off, but still no finite time algorithm. So what we can do with our cuts that we get from solving continuous subproblems is develop a finite time LP-based branch and bound algorithm. It's fair to call it a conic analog of the Quesada-Grossman algorithm, which is for convex min-LP. And I won't present the whole algorithm, but what happens is at each node of the branch and bound tree, we solve a linear programming problem where we have a finite set of K-star cuts for the cones which are nonlinear. We have some set of cones which are, these could be equality constraints or non-negativity constraints, and then we'll impose bounds based on wherever we are in the branch and bound tree. So this is this is LP that we end up solving in the branch and bound algorithm. And to prove convergence, what you need to do is add cuts whenever, subproblem cuts whenever the solution to the LP happens to satisfy integrality, and that's sufficient to say that this algorithm will converge in a finite number of steps in a theoretical sense. So that theoretical sense that I was saying is under the assumption, well, all subproblems are solved to optimality, all LPs are solved exactly, all LPs are solved exactly, and that's a little problematic because we're running things on a computer. It's not true that we'll get an exact solution to the conic subproblems or to the LPs, but what we're going to do is consider the case where we account for the LP solver having an absolute tolerance on the K-star cut. So this is a very restricted assumption. This is not full generality, but we're going to allow the LP solver to solve a relaxation of the problem where they're enforcing our K-star cuts to some absolute feasibility tolerance. And in this case, we'll be able to still develop an algorithm that converges in a finite amount of time to a solution that's globally optimal within any relative optimality tolerance, any positive optimality tolerance that you would like. And what we end up doing is, I'll skip the math, but what you have to do is when you get a K-star cut, you scale it by a certain amount, and since these are elements in a cone, you're allowed to scale the cuts by any non-negative multiplier. If you use the scaling rule and tweak the branch and bound algorithm, then we can show that under this still theoretical but a bit more realistic assumption, we can converge and get a relatively an optimal solution within some tolerance. Okay, so that's the K-star cuts framework. We have a few extensions that we developed. Very simple cases. Let's think about, let's say you have a rank K matrix, or let's say you have a rank T matrix, which is a K-star cut. A rank T matrix can be written as a sum of T rank 1 matrices. So you could actually pick apart that K-star cut into T different rank 1 cuts in the context of STP. So that's a little extension that we've played around with and proposed. Another thing is second order cone outer approximations of the PSD cone. Instead of thinking about linear outer approximations, there's some literature on second order cone outer approximations, and we relate this. You can interpret those as a infinite family of K-star cuts. And then we also account for lifting of the second order cone, which deals with an extended formulation for the second order cone. And this is potentially useful because we can deal with cases where we might need auxiliary variables in the polyhedral relaxation, but we would prefer not to have those in the conic subproblems that we solve. Okay, so some numerical experiments based on the K-star cuts framework. We selected 120 MISOCP problems from CBLib. We use the LP-based branch and bound algorithm. We implemented it using callbacks and Cplex, and it deviates a little bit from the algorithm we proposed because Cplex won't even tell us what they're doing. But we added a callback. That whenever there's a feasible solution, we'll add this cut, and that's we implement this. And we call it the MSD algorithm because the MIP solver is driving the algorithm. We had to do some post-processing. A surprising number of solutions came back that were declared optimal, came back not even being feasible, or disagreeing with objective in terms of objective values. We'll mark these as wrong. Conv in our table on the next slide means converged. Not conv means failed to converge, and failed to converge, for example, in the iterative outer approximation algorithm, that means that as soon as you repeat an assignment of integer values in your solution to the relaxation, if that repeats, because the cuts are unique based on those integer values, you can't add any more cuts. But the convergent, we haven't proven convergence, so we just stop in that case. And limit means timeout, and the time summaries will be presented as shifted geometric means with a shift of 10 seconds to account for the effect of very quick solutions. Okay, so first question we look at, I think this is one of the more interesting results we have, is we came up with this method for scaling these subproblem cuts under the assumption, and we could prove that this would give us a convergent algorithm. That algorithm is not exactly what we're doing, but we can still implement the scaling rule and see if it helps. So what we did is, I'll look at the first two rows first. If we just use Cplex as the MILP solver, MOSEC as the SOCP solver on our iterative algorithm, then by implementing the scaling, we converge on 95 as compared to 87. We decrease the number of wrong answers by 1, and we decrease the number of not convergence or failures to converge by 6. And on the solution and the problems we do solve, they end up being a bit faster because we need fewer iterations. But the wrong answers and the failures to converge are a bit problematic. So we played with disabling pre-solve on Cplex, and that seemed to account for almost all the issues we were running into. So pre-solve means that Cplex will do some internal transformations before solving the problem, and it will give you a solution to the transformed problem, which may not satisfy the tolerances you wanted on the original problem. So that's particularly the not convergence or failure to converge is particularly sensitive to objective values. So if you're a little off, that stops us from converging. But I would still say that scaling is still useful even when pre-solve is off, because the instances end up solving a little bit faster. But it's particularly useful when the MIP solver is not really satisfying its contract with the user, but the scaling ends up correcting for some of that. Another question we look at is subproblem cuts versus separation cuts. So separation cuts is analogous to the methods that are in existing solvers today. MSD separation cuts is pretty much analogous to what skip STP does for MISTP, or what these commercial solvers do for MISOCP. So if we run our, call this LP-based branch and bound with separation cuts, we solve 95 of the instances. If we replace those with subproblem cuts, we can solve 100 and even a bit faster. So at least on this family of instances, the subproblem cuts seem to do a better job than the separation cuts. In practice, it'll end up probably wanting to mix both of them as appropriate. So here's this table. You can see kind of summary statistics. If we want to see how these methods perform on different, more instance-wise, the way to read this is to go on the x-axis, go to 5 here, go up to the first line iterative separation cuts. This means that 70% of the instances solved within a factor of 5 of the fastest time. So higher is better. And there's a really nice separation here between MSD and the iterative algorithm. So we expected LP-based branch and bound. We're only solving one branch and bound tree versus solving a sequence of MIPS. That should be faster. And also subproblem cuts tends to be faster than separation cuts. And finally, we can compare Pajarito as an open source MISOCP solver. So if we take a open source MILP solver like CBC or GLPK, take an open source SOCP solver like ECOS, and for these we run our iterative algorithm because the callbacks aren't set up. It's iterative is easier to implement. And what we'll compare against is Bondman, which is a open source convex MinLP solver. It's not quite fair to Bondman because Bondman was not designed for SOCPs, but as far as I know, that's the best competition out there. We run Bondman with its, on the first line with its nonlinear branch and bound. So that was the first algorithm I mentioned. And then with iterative outer approximation, and here iterative outer approximation where we give it an automatic lifting of the second order cone just to give it an advantage. But you can see there's still a pretty huge gap between Pajarito using either CBC or GLPK and Bondman. Bondman gets failure to converge a lot. That happens oftentimes because it's trying to solve SOCPs using an NLP algorithm. They divide by 0 somewhere. It's not differentiable. Solver just stops. Wrong answers are also problematic. It's also an issue of using NLP methods for SOCP problems. And on the problems that it converged, it's basically less than half of, or around half of the problems that we're able to solve. Bondman is able to solve, and slower when it does solve. So to look by instance, here we're going to give Bondman the benefit of the doubt by taking the best of 3 on any instance. Even when you do that, it doesn't really compare to Pajarito using either CBC or GLPK. And it turns out that CBC is faster than GLPK, and also happens to be less reliable, which just kind of confirms my my intuition going into this. In some cases, CBC would return an optimal solution which didn't satisfy integrality. But that's why we post-process the results. We haven't been able to run our own comprehensive benchmark for MISTP, but Tristan Galley recently presented these results at the SIAM conference on optimization. He gave me permission to reproduce this table. So the solvers here are skip STP using its nonlinear branch and bound. So it's solving an STP at each node of the branch and bound tree. YALMIP is running the same algorithm as above, and skip STP using cut LP. That's basically the separation cuts algorithm, LP-based branch and bound using separation cuts. And for this family of instances, Pajarito is able to solve the most out of them. It's not the fastest. For this family of instances, we need to look into this a bit. It's an issue with how often we add cuts. We implemented the algorithm to add cuts only when we find a feasible integer solution, but that happens rarely for this particular family, so we might have to add cuts more often to deal with cases like this. And for this family of instances, we are second fastest solver. And I think what's interesting is that in the first column, first family of instances, we beat the nonlinear branch and bound, and the last family of instances, we beat separation cuts. So there's definitely room. There's no clear winner, and I would say that this method will be useful for some MISTP problems. Any questions so far? Okay, then let me go to the last chapter, which is work with Ilias. And the question that we're trying to address here is which non-convex constraints can be modeled with MICP. And I want to be very precise. There's a block of math here, but I want to be very precise with what I mean by modeling with MICP. So consider a closed convex set in Rn plus P plus D. and we'll identify the variables in Rn, P, and D as x, y, and z. X will end up being the space of variables that we care about. Y will end up being the some auxiliary variables, auxiliary continuous variables, and z will end up being the integer variables. And we say that our set M induces an MICP formulation of S if you intersect M with the integer lattice in the last D component and project whatever you get from the intersection onto S, and we'll call that MICP representation for S, and then we'll say that a set is MICP representable if there exists an MICP representation. If M happens to be a polyhedron, then S is actually just MILP representable. Okay, so why do we care about this particular definition? If a non-convex set S happens to be MICP representable, then the non-convex constraint X belongs to S could be enforced in an MICP problem. And MICP, you can intersect constraints. So you could end up formulating an optimization problem. This could be one small piece of an optimization problem where you optimize over this particular non-convex constraint. And if we can understand which sets are representable, then that'll help us understand what are the scope of problems that you could address using Pajarito or obviously any other MICP techniques. And we're just considering exact representations. Obviously, there's a lot you can do if you just want an approximate representation. So, for example, you could ask the question: is the set of rank 1 matrices MICP representable? That'd be very interesting because then you could optimize over the set of rank 1 matrices. What about the bilinear constraint, A times B equals C? That would also be very interesting because then you could optimize over non-convex quadratic problems. It turns out the answer is no, but at least we understand why that's the case, and we'll show a few more results along these lines.
Wait,
Yeah.
What was the question to which the answer was no?
If the set of rank 1 matrices or the bilinear constraint is representable. So neither of these are representable.
Really?
Yeah.
Okay.
At least
Let me think. Okay.
At least in an exact sense, they're not representable.
Okay, I must say, I knew the answer to the first question was no. I'm a little surprised by the answer to the second question, but keep going.
Yep.
Yeah, it's fascinating.
Cool. Okay, so this also ties into a question which Stephen Boyd asked: which non-convex functions could be incorporated into an MI-DCP framework? So if you have this DCP modeling system and you now have access to a MICP solver, you can now consider mixed integer conic representations. Well, which functions could you put in this modeling system which would translate into a mixed integer conic representation instead of a conic representation? So this is another question we'll ask and we'll answer. So to start out, we'll think about the simple case, which we'll call bounded MICP or bounded MILP. And this means precisely that there are only finitely many possible assignments to the integer variable. So this is bounded, and not in terms of the set being bounded, but in terms of the set of integer variables, possible assignments to the integer variables being bounded. So in the case of MILP, the bounded MILP, it's a standard result that if a set is bounded MILP representable, then there exists bounded polyhedra and a polyhedral cone such that S is the finite union of these bounded polyhedra plus the polyhedral cone. So these are exactly all of the non-convex sets that you can represent in bounded MILP form. For MICP, bounded MICP, there's been a little work by Sergio Suarez on a positive result. Here we have a kind of close the gap and give a complete representation that S is bounded MICP representable if and only if it's the finite union of a projection of closed convex sets. So that's the full story. If you're bounded MICP representable, then it's a finite union of projections of closed convex sets. And that's not too hard to see it's not too hard to see that you can't be more than a finite union because you have a finite number of integer assignments, and each integer assignment projects down to a convex set. So that's all you can do. What we close the gap is giving you is by giving an explicit formulation that, given any finite union, will write down a formulation. And here's the form. This is the formulation, but I won't go into the details of how this works. So for bounded MICP, you could, for example, represent the region in blue. It's the union of these two convex sets. So that's fine. You can also look at their projection. So the union of open intervals, that is MICP representable. But obviously not in terms of normal LP representations, you can't really write down open sets. So this is something that you can represent, whether it's useful in practice or whether you'll eventually run into optimization duality issues by dealing with open sets. That's a separate question, but in terms of representability, these sets are fine. Okay, so that's the full story for the bounded case. The next question we looked at is what can we gain with unbounded integer variables? So this is more on the theoretical side because the algorithms we developed make an assumption of the bounded case. We don't have a finite time algorithm that works for if there are infinitely many integer assignments, but it's still useful to understand this case. Can we represent some interesting sets? Should we try to develop algorithms for this case? So we'll see. We'll see about that. So very simple things that you can write down, which start to get interesting, is if you look at y greater than 1 over x and x being constrained to integer, you get this infinite union of slices, and the lines, I guess, rays get a little longer at each step. You could also do an infinite set of balls with growing radius, so long as the radius increases in a concave fashion, because this definition here that the norm of x minus z comma y less than f of z, this is a nice convex constraint if f is concave. So these are infinite unions of convex sets which have certain properties. So to understand what are the things that we can represent for MICP, let me recall the MILP case. To do a complete characterization, what's been studied is the rational MILP. So if you write down, if your set M that defines this formulation is a rational polyhedron, so it's written down using rational numbers, then if S is rational MILP representable, then there exists bounded rational polyhedra and integer vectors such that your set S is the finite union of these polyhedra plus, and this is a Minkowski sum, the integer cone, and this integer cone is just non-negative integer combinations of these integer vectors. So what you can do, what you get by from the in the MILP case, what you can do is you can take this finite union of polyhedra and translate them in a very regular way along a lattice, and that's about all that you can do. So to make an analog to this for the MICP case, we ended up defining something called rational MICP. I don't have time to completely motivate and give a good intuition about the definition, but this is something it took a few iterations to get to this definition. It seems here at this point it seems to be relatively stable and lets us to prove interesting things. So, and I hope it doesn't seem too restrictive. To me, it seems like a reasonable restriction on the formulation. So we start out by saying that an unbounded convex set is rationally unbounded if we can take the image of the set under any rational affine mapping, and it's either bounded or there exists a single integer vector r such that from any point in the set we can travel along that integer vector to infinity. So essentially R is a recession direction. It's an integer recession direction that's valid from any point in the convex set. And then we will say that a set is rational MICP representable if it has an MICP representation induced by the set M. And if you look at the projection onto the set of integers, so the projection onto Z, this convex set is either bounded or rationally unbounded. So this is a particular property of the set of integers that define the formulation. And okay, so this means that in the space of integer assignments, basically from any integer point, there's a single ray that we can follow to infinity, and that will end up being very useful in our proof techniques, because this will let us cover all of the feasible sets. Though I won't get to go into the proofs. Okay, so here's some properties of rational MICP, which are a little surprising. It's closed under unions, and that's surprising because rational MILP is not closed under unions. You can't take in general, you can't take a union of a rational MILP set and remain rational MILP. But it's not closed under intersections, which is interesting because rational MILP is closed under intersections. On the other hand, everything that's rational MILP is rational MICP. So there's interesting properties going on there. So here's one of our main results on rational MICP. And the starting point is, let's start out with a compact set S. So if the set we're trying to represent is compact, is bounded, doesn't go off to infinity, then if it's rational MICP representable, then S is really just a finite union of compact convex sets. So that means that if you had an unbounded number of integer variables, they were redundant, they didn't give you anything that helped you represent the set. You could have represented the set just with a finite number of integer assignments. And that means that, for example, the set 1 over n, where n increases to infinity, union 0, that's a compact set. It is not a finite union of compact convex sets, so it is not rational MICP representable. And if we look at the sets, if ABC belong to some box and such that AB equals C, then this is also not rational MICP representable, because the surface defined by AB equals C is not a finite union of convex sets. We have a stronger result that if you get rid of the box, then this set is not MICP representable, no rationality assumption. So the rationality assumption is not needed for this bilinear constraint, but it is a result of this statement here. So another example, the annulus. So a circle with an inner circle removed is definitely not rational MICP representable because it's compact, but it's not a finite union of convex sets. And we also have a separate result that the rationality assumption is not needed here. So the compactness assumption is important. We can relax it a little bit to think about epigraphs. So epigraphs of functions are not compact, but they're unbounded in a very particular direction. If we think about the epigraph over a compact domain, we can extend the previous result a bit to show that, for example, the epigraph of square root of x doesn't have a reasonable rational MICP formulation. And reasonable, we have to make one particular assumption on what the formulation looks like, but I'd say that if you knew that assumption, you would agree that it's reasonable. So you can essentially say that this set is not something that you would end up representing as rational MICP, which means that you shouldn't really hope to represent the epigraph of square root of x as a mixed integer convex feasible region. Okay, so those were previous results. We're talking about compact sets or extensions of compact sets. Here we're going to look at a set that's truly unbounded, a subset of the natural numbers, and suppose that it has infinite cardinality. Then what we can say is, well, the question we can ask is, what do we gain? We have a complete characterization for the MILP case. We know that it actually turns out to be a what you can get is a union of actually an arithmetic progression, finite union of arithmetic progressions from the rational MILP case. And you could ask, what is the convex set, convex constraint give you in terms of extra modeling power? And it turns out that the only thing that you get in terms of extra modeling power is, well, if it's rational MICP representable, if S is rational MICP representable, then there's a finite set S and a rational MILP representable set S, S sub 1, such that your set S is the union of these two sets. So the only thing that you can represent in addition to MILP is just a finite union of points. And as a corollary, the set of prime numbers is not rational MICP representable. We have a separate result. Again, this was due to Ilias. The rationality assumption is not needed here, but it does follow from this theorem. Okay, so now let's go to a little more interesting, a little more complex unbounded case and think about piecewise linear functions. So by piecewise linear functions, I'll make it very specific and say it's a function defined on the non-negative real numbers that has breakpoints only at integer values. So it's a piecewise, the function, it's continuous, its slope can only change at integer values. And let's also assume that the function takes, at the integers, it takes rational values. So you can ask, are there piecewise linear functions that are MICP representable but not MILP representable? And the answer is yes, but in a very restrictive way. It turns out that it's, again, what you can represent is just a finite, you can represent in addition to MILP as a finite subset of segments. And under the reasonable assumption that the formulation doesn't break up unit step segments. So as a set that is rational MICP, a graph of a function which is rational MICP but not rational MILP is this graph on the left. The function decreases in the first step, then it actually continues in a straight line off to infinity. This set is not rational MILP representable, but it is rational MICP representable. And an example that is not rational MICP representable, this function on the right, what I mean here is where the function f of I takes a value I squared, so the point on the parabola, integer points on the parabola, connect them with straight segments. This set is not rational MICP representable because the part that goes off to infinity is not rational MILP representable. So to conclude on representability, we gave a complete characterization of the bounded MICP case. And I would say that our results for rational MICP, you could say that it's essentially well behaved. You don't get too many surprising things. There are interesting properties about intersections and unions, but in terms of sets that you can represent, we can't represent the prime numbers. We can't represent really weird things. So what we get from going to basically from polyhedral to convex constraints, what we get is unions of convex sets and not too much more than that. And finally, for the unbounded integers, it's only useful for representing unbounded sets. If your set is bounded, you really don't need unbounded integers, which it's useful, which means that you can't have formulations that you can't represent sets that accumulate in some bounded space. So with that, I'm a little over time, so I'll take questions.
Maybe we can start with Steven's questions.
Sure. Actually, by the way, I think the the representation of the MICP working out basically what it is that's fantastic. But this is going to sound weird, but what would you do if I said I'm kind of disappointed? I was kind of hoping it to be more than that. I guess there's no way for you to answer that, right?
I'd say, yeah.
Here would be a weird question then. Like, what non-convexity would you need to introduce before you got things like, let's say, well, square root or rank 1 matrices?
Basically, the real difference is the bilinear terms. Once you can represent bilinear terms, you can represent rank 1 constraints.
Yes, and then you get everything.
Yeah, you could probably represent
Everything.
possibly represents epigraph of square root. I haven't thought about that,
Yeah.
but maybe, yeah.
Maybe complement of convex sets.
Oh, yeah,
So
okay,
it's,
yeah, okay, yeah. So another thing that would be useful is a complement of a convex set, which
Yeah.
is not necessarily a finite union, probably not. And if you
but
had,
that does it
yeah.
too. Yeah. I mean, that would do it too, right? So for example, the complement of an L2 ball would do the trick, right?
Right.
Then
Right.
you'd get like everything, wouldn't you?
Then you could probably get the bilinear terms
Yes.
out of that.
Yeah.
Yeah.
So it's interesting, right? That adding the integers. I mean, it doesn't give you much more than, you know. I was expecting the answer with integers to be everything, to be honest with you, and I'm now I see that that's wrong, of course, but it's really interesting. So would it be that you'd have to adjoin? I get something that gives you bilinear terms, I guess, right?
Yeah. So I guess these results would give you motivations to say, well, I'm not going to use integers for this because you can't.
Yeah.
Or maybe there are ways to approximate the bilinear. I mean, there are ways to approximate bilinear terms using as a finite union of convex sets.
Of course. Yeah. Yeah, but that seems like not a good way to do it, right? Actually, I don't know that. Okay. Well, actually, so for right now, I was still, you know, thinking about this quite a bit, so I don't have any other questions yet. But I have a bunch written down, and I'll cycle back to them.
Okay.
So I had a question. It really very good. So my question really it keeps cycling in and out of my brain. Hold on a minute. I just have to pick it up again. Yeah. So that when you do this, what do you call it? I call it lift and project, but you're calling it
Extended formulation.
extended formulation.
So we don't project. That's
Okay. All right. I mean, I think in my brain you're projecting, but you're not doing any computational projecting, right? Okay. But so when you do the extended, is there theory to substantiate, or is this just sort of an empirical observation that the extended formulation works so well?
So there are specific examples like that Hijazi ball example where that makes a huge difference.
Right.
In terms of like a comprehensive theory, I haven't seen results. I haven't seen very general results.
Nor have I.
Yeah.
That's no, because I was just wondering because it's just interesting that the computational difference is so extensive, and yet there's no, you know, there's nothing to back that up per se in terms of, you know, to put you on firm mathematical ground. That's all.
But also, if you're already in the conic world, and you have a small number of cones, like the second order cone, you can analyze in detail liftings of the second order cone and prove things about that. So if you have a very particular case, then you can analyze that. I haven't seen any very general theory though.
So take the very, very simple case. So I can represent my, say let n equals 100. Okay, so I've got my 100-dimensional second order cone. I can represent it directly that way, or I can represent it using, I forget if it's 50 or 99 or 101, very low dimensional second order cones. Is there any advantage to using these very low dimensional second order cones?
So I don't have the answer for if you're just trying to solve the convex problem.
Mhm.
I don't know. It's useful for polyhedral approximation because you can show that the polyhedron projects down in high space. It projects down to something much stronger in the lower dimensional space. But yeah, so I would limit my claims to say that lifting is useful if you're going to do polyhedral approximation. If you're just going to run branch and bound and solve a convex problem everywhere and never solve an LP, it's not clear that it's useful.
I mean, I have a small variety of very small comments we can discuss over the next couple of days.
Right.
That's all I got.
I mean, I can, if, can I ask another question?
Sure.
Sure. This one also is at a weird big picture level. Since you've been looking at zillions of these mixed integer cone programs or things that can be transformed into them. I was curious about, and this is more of a philosophical question. For which of these applications do you really think that that global optimization is actually needed, or useful, or very useful? I mean, what's your thinking on that story? And of course, I mean, it's got lots of. I mean, it's very vague. But what's your response?
Okay, my response would be that. So in particular applications, maybe you start out with a problem that's not even a mixed integer convex problem, and you had to make some approximations to put it into that form.
Right.
But just the fact that you can solve this class of problems more reliably, and by reliably, you need some. It helps to have some guarantees on how far you are from the optimal solution. Otherwise, there's no reason to approximate something into another form if you don't know that you'll be able to solve it better. So in a general sense, yeah.
I mean, so you're saying something like it's one less thing to worry about if at least the tough task of solving that optimization problem is done correctly.
Yes. I mean, it also, I think it's fair to say that if we expand the class of problems that we can solve to a global solution, we're also expanding the class of problems that we can do well heuristically on.
Okay. And that's by early termination?
Early termination, or more reliably solving a certain subproblem that's maybe not the full problem that you cared about. Yeah, so that would be my response.
Okay. Good.
I guess my question is kind of a follow-up to that. How much faster do you think Pajarito would be if you just, let's say, fix the optimality tolerance to 1% cap?
Yeah. Very
Okay, it's hard to say, but it's an option, so you can just solve your problem and set it to 1% gap. Yes, there's probably, it could cut off. There is some tail on the iterations where it takes you get to a small gap, and then it takes a few more iterations to close the gap. So could easily cut off 20% of the iterations, a third of them. Possibly not too much more than that.
What about 10%?
So I think it'd be interesting to, an interesting question is if you can study the iterative algorithm and put a bound on how many iterations you need to solve a certain class of problems. So we don't have any, the only bound we have is finite. It has to be finite iterations, but I would bet that for particular classes of problems that you could show that it only needs, you could prove some sort of convergence rate. No, it could be polynomial because each step is solving MILP. Yeah, so there's no P equals NP issues. So I'd say that'd be an interesting research direction.
Good, because that was my other question. What would be an interesting direction?
Well, look, there's on top of that, there's a lot of directions using using MICP as now that we know the limits of MICP, there are problems beyond that limits, and we could figure out what's a reasonable way to approximate them using MICP, or show that it's not a reasonable thing to do, but hasn't been really looked at yet.
I guess we're running a little bit late, so maybe we'll hold off for questions to the public for afterwards. I guess now the committee needs to deliberate, so we'll ask everybody to step outside for a little bit.
Let me make a
Couple questions.
Okay. Well, no, what about this? Instead of everybody having to leave this room, we could just convene in my office.
Oh.
Oh, we've got Steve
problem
here.
is Steve.
Oh, okay.